When movies and television depict a tsunami, they usually show the exact same thing: a gigantic, sharply curling wave that towers over a city skyline like an oversized surfer's paradise before crashing down onto the streets. But physical reality looks entirely different. A true tsunami doesn't arrive as a localized, crashing peak. It behaves like an unrelenting, fast-moving plateau of surging water, a sudden, massive rise in sea level that simply refuses to stop pushing inland. Looking at this side-by-side cross-section, you can see the difference in how energy travels. Normal, wind-driven surface waves generate a shallow, circular energy loop that only affects the top layer of the water. A tsunami, however, is a massive block of kinetic energy that displaces the entire vertical column of the ocean, from the seabed all the way to the surface. Because it moves the whole water column rather than just the surface, a tsunami completely defies our intuitive understanding of how ocean waves are supposed to behave. That sheer volume of moving mass is what makes it uniquely destructive. To find the energy required to move that much water, we have to look down to the abyssal depths of the ocean floor. Here, at massive tectonic boundaries, the Earth's oceanic plates are constantly grinding against continental plates. This area of intersection is called a subduction zone. One heavy tectonic plate gets caught and dragged beneath another. As the rock locks together, it builds up immense physical stress over the course of centuries. Eventually, that friction is overcome. The overriding tectonic plate violently snaps upward. This is a megathrust earthquake, physically reshaping the ocean floor in an instant. When that seabed jolts upward, it acts like a colossal piston. It instantly thrusts the entire vertical column of water sitting directly above it towards the sky. This means a tsunami has absolutely nothing to do with the weather above. It is the direct result of a sudden, massive geographical restructuring of the Earth, locking an unfathomable amount of kinetic energy straight into the ocean. Up on the surface of the open ocean, that catastrophic energy release is almost invisible. If you were sitting in a boat directly over the earthquake, you likely wouldn't even notice the wave passing beneath you. This chart shows why. A storm wave's wavelength, distance between crests, is hundreds of feet. A tsunami stretches hundreds of miles, but its actual height is tiny, spread so thin it's only feet tall, yet it cruises at 500 miles per hour, matching a jet airliner. The immense depth of the open ocean hides the wave's true power. It operates as a high-speed ghost wave, traveling invisibly until the physical environment around it changes. That change occurs when the wave finally leaves the deep ocean and makes contact with the rising incline of the continental shelf. Hitting the coastal incline, the wave's bottom scrapes the seafloor. Intense friction drastically slows the front edge. But energy cannot disappear. The fast back end catches up. This is the shoaling effect. Hundreds of horizontal miles compress, forcing a towering vertical rise. Depending on how the seabed shifted, the leading edge of the wave might actually be a trough, not a crest. When a trough hits the shore first, it causes drawback. The ocean dramatically sucks away from the beach, exposing bare, wet seabed. The shallow coastline itself is what turns the wave into a weapon. It utilizes the physics of the shoaling effect to transform hidden, deep-water speed into a visible wall of destruction. At the moment of impact, the wave does not crash and quickly recede like a normal tide. Because of that massive trailing wavelength, pushing from behind, it violently maintains its forward momentum. This is inundation. The water acts as a continuous, surging river, driven by the sheer mass of the ocean, flowing inland at high speeds for several minutes. Understanding exactly how speed, wavelength, and the shoaling effect interact allows structural engineers and seismologists to calculate precise risk models. They use these mathematical relationships to deploy early warning buoy systems across the globe, buying coastal populations vital minutes. A tsunami is an entire displaced ocean looking for a place to go. If you are ever on a beach and see the water unnaturally pull away from shore, the devastating physics of shoaling are already in motion. Your only option is to immediately seek high ground.